Practicum 7 of Computer Organization and Architecture. In this experiment, we analyze how cache memory works and how different cache mapping techniques affect the performance of a computer system. Cache memory is a small, high-speed memory location close to the CPU. Its main purpose is to store frequently used data so that the processor can access it faster than the main memory. The first program demonstrates direct cache mapping. In this method, each memory can be placed in one specific location. The cache index is calculated using the modulo operator, block number, mod cache size. The program checks whether the requested memory block is already present in the cache position. If it is present, it is called cache int. If it is not present, it becomes cache miss. So the second program demonstrates fully associative cache memory. Unlike direct mapping, any memory block can be placed in any cache line. The program searches the entire cache to check whether the block exists or not. If the block is found, it is it. Otherwise, it is miss. The block is inverted into the cache. This method reduces the conflict but requires more searching, which makes the implementation slightly slow. The third program shows set associative cache mapping, which is a combination of direct and associative mapping. In this method, the cache is divided into multiple sets and each set contains multiple cache lines. A memory block is mapped to a specific set, but it can be stored in any line within that set. This approach balances the simplicity of direct mapping and the flexibility of associative mapping. So the fourth and fifth program calculates cache int ratio and cache miss ratio. The int ratio is the proportion of memory access that are successfully found in RAM, while the miss ratio is the proportion of access that are not found in the cache. These metrics help the efficiency of the cache system. So this is miss ratio and this is int ratio. So the sixth program demonstrates memory block to cache line mapping. It shows how different memory blocks are mapped to specific cache lines using the modulo operator. This helps visualize how memory addresses are distributed across the cache. So the seventh program focuses on cache initialization. Before using the cache, it must be initialized with empty values. In this code, the cache array is filled with -1 to index that the cache lines are empty. So the eighth program simulates random memory access pattern. In real computer system, memory access are not always sequential. This program generates random memory block requests to mimic real CPU behavior and observe how cache performs change with unpredictable access pattern. So the ninth program implements FIFO cache replacement, which stands for first in, first out. When the cache becomes full, the old block in the cache is replaced by the new incoming block. This method is simple to implement but does not always provide the best performance of a computer system. So the final 10th program demonstrates a simple version of LRU, replacement policy, which stands for least recently used. In this method, the block that has not been used for a longest time is removed from the cache when new data needs to be stored. This approach is widely used in modern processors because it improves the cache hit rate. Overall, these programs helps us understand the working of cache memory, mapping techniques, and replacement properties. Thank you.